In this video, I'm going to be building a low-powered Armstrong oscillator circuit, which is really just a circuit that generates a signal, and that signal operates at a fixed frequency, which is dependent on the components used for the Armstrong oscillator circuit. Before I built the Armstrong oscillator circuit, I decided to use a software called LT-Spice, which allows you to design your own circuit. And when I simulated my circuit, I initially wanted to have a stable frequency at 2 megahertz. And so I ran the simulation in Spice, and I'll show you guys the results that I got and how I built it in Spice. And so what this does is it's basically a transistor which is connected to an LC tank circuit and also connected to a feedback inductor. And what happens is the feedback inductor induces a voltage into the tank inductor, and this tank inductor then resonates with the capacitor. And now that it's resonating at a certain frequency, it then does the exact same. It resonates the same voltage across the inductor based on electromagnetic induction. So the change in current in this inductor is going to induce a change in current in this inductor. And because it's operating at a 2 megahertz frequency according to my calculations, this inductor should be swinging its base voltage at a 2 megahertz signal. And this then feeds past the coupling capacitor, which basically blocks the 12 volt DC supply and allows for the lower voltage AC supply. And this then feeds into the base of the NPN transistor, and it oscillates at a 2 megahertz signal. So when I run the simulation, you can see here I get a stable oscillation of around 2 megahertz. In this case, it isn't 2 megahertz because LT Spice takes account of the transistor. So if I go across here, you can see here peak to peak that the frequency is around 1.7 megahertz on the bottom left. And yeah, so this does take into account some real world effects, but when I ran the simulation, when I ran this in real life, obviously there was part losses that happened. When I went to build my Armstrong oscillator circuit, I had to build an inductor, the tank inductor and the feedback inductor, or the tickler inductor, whichever terminology you use. Basically, the way I measured it was I used a calculation, which apparently puts the inductor value 95 percentile of what it actually is. So as I needed a 10 microhenry inductor for the tank inductor, what I did was I calculated the size, length, diameter, and the number of turns I needed. I then 3D printed a bobbin and I ran the copper wire on the bobbin pin. So when I measured it with my LCI meter, I got 10 microhenries. And then for my 2 microhenry feedback inductor, all I did was just did the exact same thing, but I did 1/5 of the turns that I did on my 10 microhenry inductor. And that way I should approximately get 2 microhenries. And when I went to measure it on my LCI meter, it was around 2.2 microhenries and like 9.9 microhenries, about basically 10 microhenries. And as you can see from the picture here, this is the circuit that I had built. As you can see here, guys, I built the Armstrong oscillator circuit that I designed for 2 megahertz signal frequency. And when I built it, I had many troubles, so I could not get any signal from it. So what I did was I wrapped around the coils together, and I wrapped it around in tape. You can see the green and white tape, and I put them on top of each other, so it wasn't inducing a voltage across one. And as I tested it, I still didn't get any signals even after I did this. So the main reason behind why I don't think I was getting a signal was because I was operating it at 2 megahertz, and because I was using a normal breadboard for the 2 megahertz signal, there was a lot of strain ductance, and there was strain ductance from the wires as well. And at a very high frequency with strain ductance, there's going to be a lot of inductive reactance, which is basically just resistance that's generated from the wire, which you can see from the breadboard. The resistance from the wire was just too large, so I wasn't getting any voltage across it because of the voltage drop between the inductor. So I then decided, as you can see in the background, to build a lower frequency oscillator, and I made the coil a lot bigger, as you can see. The reason for making the coil a lot bigger was so I can get a greater voltage induced into it. Not just that, I can also manage the frequency. So I then changed the inductor to that massive inductor around the PVC pipe, and I did a lot of turns, approximately like 700 turns. And then for the feedback, as you can see here, I lowered the turns by like a fair amount. As you guys can see here, these aren't proper LC oscillations. They're actually LC oscillations that are dying down. and the reason for this is actually, I'm not fully sure, but I noticed something interesting is when I touch the wire and squeeze it, I actually get a stable oscillation frequency of 60 kilohertz, which is what I was trying to aim for. I'm not fully sure why this is, but I noticed this was a problem, and so I spent many ways to troubleshoot this. I didn't know what the problem was. I mean, I tried literally everything. I asked ChatGPT. I even changed the power supply, and that didn't work. So I had no idea whatsoever. The main thing that I did to try to troubleshoot this problem was I shortened the wire length from the feedback coil and the tank coil, and this did actually seem to help my results and it being more consistent and having a stable oscillation frequency. But I still had this problem, and you know, if I had to take a guess, since when I squeezed the wire, the stable frequency was there, I believe there to be some sort of interference within the circuit. Not fully sure why, but if anyone knows, please just leave a comment and explain why. But yeah, I mean, I tried a lot of stuff to try to troubleshoot this problem, and nothing was really coming up. So I mean, eventually the oscillations were stable. After I'm not fully sure what I did, but I changed the wire length and made it shorter. I squeezed the wire as well. I even moved the power supply unit up and down, and that sometimes made the frequency stable, but I'm not fully sure why. As you guys can see here, I've finished the this mini prototype of a Armstrong oscillator. The main reason behind doing this is because I'm going to make a more powerful one while using a vacuum tube amplifier, and I'll put that in my next video. The only difference in this Armstrong oscillator is instead of the transistor, I'm going to be using a power triode vacuum tube. It's a 3-500Z vacuum tube. It's going to be operating at a high frequency of around 24 megahertz, and the reason I'm doing this is because when I designed the antenna, I can make it at a shorter length, and by making it at a shorter length, it just helps in having a smaller workspace that I can use. Another reason, well, I mean, this is more of a downside to using a high frequency, but it means that I have to make sure that the circuit is properly matched and tuned. So I'm going to have to use a pi filter, stuff like that. I'll show you guys in the next video. Anyway, as you can see here, this is the vacuum tube. Basically what I just done here is a small mini version of an Armstrong oscillator, so I can build a more powerful one. And as you guys can see, this is some footage for my next video. I've currently built the power supply. I've literally made it out of purely broken parts, including the microwave transformer, the 9 capacitors I've used here, which is also in series with an inductor. This is done to create a pi filter. Basically just keeps the rectified voltage at DC, just voltage ripples to actually minimize the voltage ripple and provide a constant plate voltage of 3000 volts. If you also notice, the transformer is in a acrylic kind of case, and underneath the acrylic case is a full bridge rectifier made purely out of vacuum tube diodes. So anyway, you guys, I also made a spark gap, as you guys can see. I'll show you guys the spark. This spark gap is just me testing the power supply to see if I can get, you know, at least over 1 kilovolts DC. And then after I found out I had that kilovolts DC, I tested it with the oscilloscope, and I did get 3 volts DC on the oscilloscope power supply with my 1 to 1000 voltage divider. So anyway, this is the end of the video. I hope you guys enjoyed.